Hi guys, I am Biji, and in this video we shall learn about enzymes. Enzymes, as you know, are biological catalysts, which means they speed up chemical reactions that occur inside our body and also in other living systems. But how do they do that? We'll come to that very soon. First, let's talk about chemical reactions. Chemical reactions that occur inside our body are pretty much like chemical reactions that occur elsewhere. They can be of two types. One is exergonic reactions, that is, they release energy, and the other is endergonic reactions, that is, it requires an input of energy. The root word here is ergon, which means work. Work in science is anything that utilizes energy, and in this scenario, it is a chemical reaction. So exergonic reactions release energy during a chemical reaction, and endergonic reactions require an input of energy for the chemical reaction to occur, which means compounds have some sort of energy for them to give and take. High energy compounds give away energy and form low energy compounds, whereas low energy compounds will take in energy and form high energy compounds. And there's a term for this energy. It is called free energy. Free energy is the amount of energy that is available to do useful work. Now, one way to wrap your head around this free energy concept is to compare it to potential energy. Potential energy is something that an object has due to its mass and its height. So, an object that is placed on top of an inclined plane has a higher potential energy than something that is at the base of it. Also, a heavier object has higher potential energy than a smaller object. So if we were to place an object on top of an inclined plane, it would come hurtling down quite spontaneously due to the gravitational forces. Similarly, some compounds have higher free energy than others. Now, if you're wondering why that is so, very good. But unfortunately, that is not pertaining to this discussion. We shall talk about that in another video. Meanwhile, I would encourage you to look it up. But for this discussion, it would suffice to know that some compounds have higher free energy and are more unstable than other compounds that have lesser free energy and are more stable. And the high energy compounds would transform itself to low energy compounds quite spontaneously, releasing energy. And these are your exergonic reactions. Now, endergonic reactions, however, do not proceed spontaneously, and they occur inside our body only when coupled to exergonic reactions. What do I mean by coupled? It means that the energy released from an exergonic reaction will drive the endergonic reaction. We can understand this too by going back to our analogy. The heavy object on top of an inclined plane will slide down the plane spontaneously. Now, if we connect this to a smaller object using a suitable pulley and string, then the energy from the falling can be used to lift the small object up the slope. Greater the elevation, greater the amount of energy that will be released, and greater the amount of work that can be done by it. Similarly, we can imagine the exergonic reaction as going downhill, driving the endergonic reaction, which is going uphill, provided the energy that is required here is lesser than what is being released. For example, let's consider one of the fundamental reactions of the metabolic pathway, the phosphorylation of glucose to glucose 6-phosphate. This is the first step of glycolysis, and it is an energy requiring reaction. It requires 13.8 kilojoules of energy. But this reaction can be made feasible by coupling it to ATP hydrolysis. When ATP breaks down to ADP and a phosphate group, it releases lots of energy, about 30.5 kilojoules of energy. So by coupling these two reactions, the resulting reaction will be an exergonic one, and that releases about 30.5 minus 13.8, that is about 16.7 kilojoules of energy. So in this way, most reactions that take place inside living system are exergonic, because even the endergonic reactions are coupled to a highly energy releasing exergonic reaction. So with that, you probably have a fairly good idea about how chemical reactions occur inside your body. But how feasible a reaction is does not determine how quickly the reaction will proceed. Even highly exergonic reactions need not take place at a time scale that is noticeable. For example, sugar is a major source of energy inside our body, and we routinely break up sugar in presence of oxygen to release huge amounts of energy. Yet you can leave sugar lying around open to oxygen on your shelves without any worry of it burning up. Why is that? Let's try to understand this by seeing how the free energy changes during this chemical reaction. So let's assume this is the free energies of the reactants. Of course, it's the summation. So this is the sum of the free energies of the reactants, and after a while it will form products. And since this is an exergonic reaction, the free energies of the products will be lower than the free energies of the reactants. So you might assume the reaction proceeds something like this, like a slope. But actually it doesn't. It would look more like this. So as you can see, there's a barrier. And this barrier is formed because there's a huge amount of energy required for the reactants to combine together. They combine and they form this intermediate, which has a higher free energy than the reactants or the products. And this high energy intermediate is the reason for the barrier. It's called the activation barrier. So some reactions have higher activation barriers than some others. And the breakdown of sugar has a huge activation barrier, which is why you do not see sugar burning up spontaneously on your shelves. Now, do every chemical reaction have such an activation barrier? Yes. Every single chemical reaction has an activation barrier. Even endergonic reactions would look more like this. The products have a higher free energy than the reactants, and the intermediate complex has even higher energy. This is because chemical reactions require breaking of existing bonds for the formation of new ones. And breaking existing bonds mean distortion, which requires energy. And this distorted state is what you call the intermediate complex or the transition state. And like I mentioned, it is highly unstable and has a very high free energy. So most chemical reactions would not occur at a measurable rate without an energy input. And the energy that is required to surmount this transition state or cross this activation barrier is called activation energy. Every chemical reaction is a result of productive collision between the reactants. The reactant molecules have a certain amount of kinetic energy and are moving around and will collide with each other. While many such collisions are possible, only the collisions with the right amount of energy and in the right orientation will form the transition state complex. Or in other words, only the molecules that acquire the kinetic energy equaling the activation energy will form products. So how do molecules do this? How do they acquire this energy? One way is through heating. So heating increases the kinetic energy of all the molecules and they start moving around more rapidly, which means it will increase the frequency of their collision. And increasing the frequency of collision will increase the chances of a productive collision. If heat is the means to cross the activation barrier, then how does the human body, which functions at constant temperature, use sugar as fuel regularly? Definitely heating is not an option for us, not unless we plan to get cooked. Nor do we wait years together to break down 1 mole of sugar. So then what's the trick? Well, this is where enzymes come in. Enzymes enable chemical reactions to occur at a biologically relevant time scale. And they do this by bringing the substrates together in the right orientation so that there can be an effective interaction. So the substrate binds the enzyme in a specific pocket called the active site. And they sort of fit together like a jigsaw puzzle. This interaction is very specific. Most enzymes do not bind any other substrate. And once the enzyme binds the substrate, it forms the enzyme-substrate complex, which is stabilized by many different interactions between the enzyme and the substrate. The enzyme can then undergo a conformation change or a small change in its shape so that it can stabilize the transition state complex, which will then break down and release the product. So it is very important to remember that the enzyme is not used up in this interaction and it is completely regenerated. After the product is formed, the enzyme goes back to its initial conformation state. How does the free energy graph look like when enzymes join the party? Like I already mentioned, what the enzyme does is it stabilizes the transition state, or in other words, it decreases the free energy of the transition state. So this lowers the activation barrier itself. The complex that is formed still has a higher free energy than the reactants or the products, but it has considerably lesser free energy than the enzyme-free transition complex. This way it enables chemical reactions to come together successfully, and the probability of them forming the product increases. This hastens the chemical reaction. Without enzymes, virtually no cell reaction would occur at a useful time scale. If it is still not clear how enzymes hasten a chemical reaction, let me explain it to you with a simple analogy. Imagine you and your friends are doing a high jump. Which bar are you more likely to jump across? A 2 feet bar or a 5 feet bar? The 2 feet bar, of course. The actual time that may be required to cross either of this may not be very different. But if all of you must cross the 5 feet bar, that would require a lot of time and training. It is the same with chemical reactions. The activation barriers are like the high jump bars. Some molecules may have the energy that is required to cross the activation barrier, but most molecules require a prep time to obtain this energy, especially if the activation barriers are pretty high. And the rate of a chemical reaction is dependent on how soon the molecules cross the activation barrier. If the activation barrier is low, then the energy required by the molecules to cross this is lesser, and more molecules are likely to cross it sooner. And this way, the products are formed faster. So, enzymes hasten chemical reactions by lowering the bar. There's one more thing the enzyme does. We spoke about how endergonic reactions are coupled to exergonic reactions inside biological systems. And we discussed this using the analogy of a high potential energy object sliding down the slope being able to lift a smaller object up the slope. We said this was possible if they are connected using a suitable pulley and string. The pulley and string in biological reactions are enzymes. Enzymes store in them the energy released from the exergonic reaction and utilize this to drive the endergonic reaction. So that's all, guys. Hope this has given you some insight on how to view the molecular world of enzymes. And if this has helped you, please let me know and subscribe to my channel. I'll be coming back with more such cool learnings.